In this lesson, we'll go over the definition of secant lines and review how to solve certain equations. So to start with, as a definition, a secant line is a line that intersects a given curve more than once. Let's check that out in example 1. Here I have the curve y is equal to x squared, this parabola, and I'm going to choose 2 points on it, P and Q, the point 0, 0 and the point 1, 1. I'm going to label them. So here's the point P, and here's the point Q. If I draw a line through these 2 points, I get this thing here, this is a secant line because it intersects the equation twice, which is more than once. Here are a couple of questions about this given secant line. First, can we find the slope of this line? And also, what is the equation of this line as well? Let's start with slope, typically denoted by the letter m. It's defined as y2 minus y1 over x2 minus x1. Here, x1, y1 and x2, y2 refer to a couple of points. So like this could be x1, y1, and this could be x2, y2. And once you have these things, you can put that information into this formula to figure out what the slope is. So let's do that. The slope is equal to, all right, this is y2 and this is y1. So we get 1 minus 0, all divided by, and we get the same thing for x2 and x1. Here's x2, here's x1. It's also 1 minus 0. This simplifies very easily to just, 1 over 1 or 1. And for this line, the slope is 1. Now that tells you something about the line. If your slope is positive, it means your line is increasing. And the larger the number is, the steeper the line becomes. If a slope is 0, it's horizontal. And if it's a negative number, then it's a decreasing line. So this is the formal definition for slope, but there's one that's a little bit more informal, and that is rise divided by run. What this means is if you pick one point on a line, how far you go up is your rise, and how far you go over is your run. And if you divide those two numbers, that will tell you the slope. So how do you go from one point to another? The rise is 1. That's where this 1 comes from. And the run is also 1. And you divide those two numbers, and again, you get a slope of 1 as well. So really, you can use either of these, although this one can be useful if you don't have a graph. Now, the second thing is, that's the slope. What about the actual equation of this line? There are 2 different equations that we can use. One is called the point slope formula. And you can use this whenever you have the slope and 1 point on a given line. And the formula is y minus y1 is equal to m times x minus x1. So x1, y1 is your point and m is your slope. Here we know the slope is 1. You can choose any point that you want. I'll choose this one because it's more simple. If I put this information into this formula, we get the following. Y minus 0 is equal to 1 times x minus 0. This simplifies nicely to just y. I don't need that 1 or the 0. I can just put x, and you get the line y is equal to x, which makes sense. This line goes through the origin, and its slope is 1. The other formula that you can use to find the equation of a line is the slope-intercept formula. And intercept meaning the y-intercept. And if you're familiar with this formula, it's of the form y is equal to m times x plus b, where b is the y value of your y-intercept. The y-intercept is clearly 0, so you'd put a 0 here. We already figured out that the slope is 1, so you'd put a 1 here. And we end up with the same equation. You still get that y is equal to x is the equation of the secant line. But that's pretty much it. So we'll have to use the formula for slope quite a bit in this class, and it'll also be useful to figure out the equation of a line, and you can use either of these formulas to do so. Just a couple of other thoughts with this example. Again, where we're working with the curve y is equal to x squared, this parabola. Is every line that you draw in the xy plane a secant line? And the answer is, well, no, that's not true. Just a couple of examples to look at. If I choose this graph over here, You could draw a vertical line at x is equal to -1. So I'll draw that on here like this. So it goes down like that. This vertical line will only intersect the parabola here at this point. So it's only once, and the secant line has to go through the curve more than once. So here we have a vertical line. Now, what is the equation of this vertical line? It doesn't fall into the formulas that we had on the previous page. Here, a vertical line is always of the form x is equal to some number. So for this graph here, it's actually x is equal to -1. And the reason for this is the x values on this line are always -1, and the y values can be anything. So another example of something that is not a secant line would be, well, how about a horizontal line that doesn't even intersect the graph? So I could draw something like, I don't know, something like this. So here's a horizontal line. It never actually meets the curve ever. So this would not be a secant line to this curve either. So a horizontal line. Now what's the formula of this line? Horizontal lines will always be of the form y is equal to some number. And in this case, the y value that we're referring to is y is equal to -1 this time. So again, y on this line is always -1, and the x values can be anything. So there's one other type of line I'd like to talk about that is not a secant line, and that's something called a tangent line. We'll carefully define this in future lessons, but just to get an intuitive idea of what this is, here's an example of a tangent line. I'm going to choose a point on my curve, and this is the point 1, 1. There are a lot of lines that can go through this point, but there is exactly one line that is tangent to this curve at this point. It's going to intersect this one spot, but it's also going to move in the direction of the curve. You could think of it as like holding up a ruler to the curve at this one point. That straight edge would be tangent to the equation, so I'll draw this in here. So here is a tangent line. I'm not sure what its slope is or even what its formula is equal to, but I can draw it. At this one spot, this line will intersect the graph only once, and it is moving in the direction of the curve at this point. We're going to spend a lot of time focusing on these particular lines and how to compute their slopes, but I'd like you to have an intuitive idea of what a tangent line is, and I'll leave it at that for now. Here in example 2, we have a function which is 7 minus x squared, another parabola. The goal is to find the points where the secant line g of x is equal to x plus 1 intersects the function f. Now here I have a graph of what's going on here. This is the equation 7 minus x squared, so I'm going to label this thing as f. And x plus 1 has got to be this equation here, which is g. And the goal is to figure out, well, I can see that there are 2 points where these equations meet. I can actually figure out what those points are, and how would you go about doing that? The trick is to take your 2 functions, f and g, and set them equal to each other. What you'll do is have an equation that depends only on x, and if you solve it, it'll tell you the x values of these 2 points. So f of x is 7 minus x squared, and g of x is x plus 1. How do you go about solving this? When you have a quadratic, there's several ways. You could set this equal to 0 and then factor. You could use the quadratic formula. There's another method called completing the square, and sometimes you are allowed to use square roots to solve quadratics as well. However, for this one here, I'm going to take the approach of, I'm going to move all of this stuff to this side of the equation, so I have 0 on this side. I will factor this side and set each factor equal to 0. That will look like this. I'm going to subtract 7 from both sides, and I'm going to add x squared to both sides. In doing so, on the left, I definitely have 0. On the right, I added x squared. X is already there. Now we have 1, and we're really subtracting 7, so that gives us -6. can we factor the right side of this equation? And the answer is, I think, yes. You'd have to have an x and an x to multiply to an x squared. The last term is negative, which means you'd have to have a positive and a negative. We now need two numbers that multiply to -6, yet add to a positive 1. And I think the only choice would be 3 and -2. The product is definitely -6. The sum of those two numbers is +1. From here, you can take each factor, in this case x plus 3, and x minus 2, we don't need the parentheses anymore, and we can set it equal to 0. To solve them for x, on this one you could subtract 3, so you get x is equal to -3. And here you could add 2. Now, these values are the x values. This one has to be 2, and this one has to be -3. But what are the actual, in this case, we're looking for points. So not just x values, but x and y values. To figure out the corresponding y values, you can use either f or g to solve for that. Since g is simpler, I'm going to use g. So I'm going to take the function g. I'll first put in -3. So g of -3 is -3 plus 1, and that is g of -3 is equal to -2. So my point is -3 for x and -2 for y. And that is referring to this x value and this y value of -2. I could have used the function f to get the y value. I chose g just because the equation is simpler. I'll do the same thing for this x value of 2. If I put 2 into the function g, it should tell me the y value here. G of 2 is 2 plus 1, which is 3. And so I have the point 2 for x and 3 for y. These are the 2 points that we're looking for. Now, there is one other thing that is happening in this question. It says, using this information, determine where the function f is less than, strictly less than the function g. With a graph and this information, this question should be relatively simple. Here's why. This is asking, where's the y values of this function less than the y values of this function? Since there are only x's that appear within this equation, you can record your answer using x values. So here's where they're equal, and that's not what I'm looking for. So here's a part of the graph. If I look at the y values of f here, are they less than the y values of the function g here? And the answer is no. These are above all of these corresponding values. You have to go up to go from the function g to the function f. That is not what less than means. You'd actually want the opposite to be true. What about this spot over here? Okay, here the function f is less than the corresponding parts of the function g because you have to go down. So here, f is actually less than g. I'm going to highlight it. Are there any other spots on the graph where this is true? And the answer is, well, yeah, over here. This is f. This is g. F is lower than g, so that means less than. So I have this stuff as well. I mean, technically we did answer this question, but what are the x values for which this is true? It's not this stuff in the middle, because that's referring to this portion of the graph. We want the x values here and the x values here. So to wrap this up, if you want to know where f of x is less than g of x, there's two places. When you're from -infinity to -3, and also when you're from 2 to infinity. So here I'm using interval notation. If you use a parenthesis, it means you don't include the point, and if you use a bracket, you do include the point. If you ever have infinity or -infinity, you would never use a bracket, you would only ever use a parenthesis. You can also use the symbol U, which stands for union, if you want to connect a couple of different intervals together and say, well, this is all the answer. This is the only way to write it. You can use this approach. But this is the answer where the function f is strictly less than the function g. If there were an equal sign here, we'd want to include -3 and +2 with brackets, but that is it for this problem. Okay, so we've solved a couple of equations using quadratics. What about a trig function like this one? Let z of theta be 2 sine of theta, and that is this graph here. It's a sine curve. It goes forever in both directions, and it has a period of 2 pi. Starts here, ends here, and it's this cycle that is copied and pasted in both directions. Here I have y of theta is equal to 1, which is this horizontal line, and I want to figure out all of the intersection points, and specifically when we're between negative 2 pi and positive 2 pi. If you sketch a graph, you can actually see there's 1, 2, 3, 4 places where this is true. This one won't be our answer because it looks like it is beyond 2 pi, so there should be 4 answers that we're looking for. How do we go about finding them? The same way we did in the previous problem, where you would take one function, z of theta, and set it equal to the other, which is y of theta. And just to be clear, the blue function is z, and the red function is y. I will substitute in their actual formulas. So z of theta is 2 sine of theta, and y of theta is just the number 1. So it really looks like this problem is just a matter of solving the equation. Sine of theta is equal to a half. Anytime you're trying to solve a trig equation, try isolating the trig function. But where do we go from here? This is where we need some background knowledge. That is, we should have no angles where sine equals specific numbers, like a half, or maybe root 2 over 2, or root 3 over 2, and so on. So here you actually have to recall some background knowledge. Do you know an angle where sine is equal to a half? And we'll record our answer in radians. So you might recall this answer as, oh, okay, well, theta is 30 degrees. And that's great. In degrees, certainly sine is equal to a half. The corresponding radian measurement is pi over 6. So here it is. This is one angle where sine is equal to a half. And that is exactly this spot right here. Now, there's 1, 2, 3 others. How do you figure those out? I'll put as a fact that sine has a period of 2 pi. And that means if you add or subtract 2 pi from any point, you end up back where you started. So 2 pi is, if you add it, it will take you to this spot here. I don't care about this point because it's outside of our interval, but if you subtract 2 pi, you get this spot right here. So let's find that one. So what is this angle here? What you can do is, okay, we can take pi over 6 and subtract 2 pi. Basically, I think we can simplify this answer by saying, well, okay, we have pi over 6. I'll put this into one fraction. I want a common denominator of 6, which means I have to multiply the numerator by 6, which is 12. And this is really 1 pi minus 12 pi over 6. That's negative 11 pi over 6. And that is this spot right here. This is negative 11 pi over 6. Okay, so I have 1, 2. If I can figure out this one, I can subtract 2 pi from it to get this one. So the real question is, how can I figure out this spot here? So how do I get this? I'm going to draw a unit circle and maybe use that as a guide to figure out what's going on here. Here's another way to think about just the function sine. And that's if you look at a unit circle. On a unit circle, if you start here, this is 0 radians. And you can count by pi over 2. So this is pi over 2 radians. This is pi radians. 3 pi over 2 radians. And then this is actually back to 2 pi radians. Sine is defined as the y values for a given angle on the unit circle. So for example, if you draw a 30-degree angle, or in radians, pi over 6, you get this angle here, and the y value is a half. So here we have an angle of pi over 6, and sine is equal to a half there. If you go from the first to the second quadrant, there's another angle where sine is going to equal a half. And I'll draw that in here like this. And the question is, well, what is that angle? whatever that angle is will correspond to this spot right here. You can use symmetry to figure this out. If you're at pi radians, if you go backwards pi over 6, that has to be this angle measurement here. Let's do that. So let's see here. It'll be pi minus pi over 6. Pi is also 6 pi over 6. And if you subtract pi over 6 from 6 pi over 6, you get 5 pi over 6. And that's this angle here. This leaves us with one angle, and that's this one here. The way you can get to it is by subtracting 2 pi from 5 pi over 6. On your unit circle, you can think of it as rotating one full turn backwards 2 pi. So let's see. We'll get this one, and that'll answer this problem for us. So that's this spot right here. If you want that, that is 5 pi over 6, but you're subtracting 2 pi. Again, I'm going to write 2 pi as 12 pi over 6. And 5 pi minus 12 pi is negative 7 pi over 6. And that is this angle here. That's negative 7 pi over 6. This is a good problem to look at because trig functions can be quite complicated. You have to know some background knowledge, though, to solve these equations. So when dealing with things like sine, cosine, or tangent, if you set them equal to a number, it'll probably be some number that you have an answer to. But after that, you have to use further knowledge to maybe find more answers by adding or subtracting values of 2 pi. But that is it for this problem. Okay, so we've looked at quadratics, which are polynomials, trig function. The last function I want to focus on is absolute value functions. So here I'm starting with a function h of t is equal to negative the absolute value of t minus 2 plus 3. So maybe just a reminder about how absolute value works. Instead of giving a formal definition for it, I'd like to explain it maybe with a quick example. Like, what is the absolute value of 5? What the absolute value function does is if you put in a positive number, that number stays positive. However, if you put in a negative number, like negative 3, it returns a positive value. So positive goes to positive, negative becomes positive, and if you put in 0, it just gives you 0 back. You can think of an absolute value as distance traveled on a number line. So if you're at the location of 0, the distance you've traveled is 0. If you move 5 places to the right, well, you travel the distance of 5. But if you go 3 places to the left from 0, you're at negative 3, but the actual distance you traveled is positive 3. That all being said, here we have the function h of t is equal to this thing. And I want to find all values of t where this function intersects this function, negative 1. So here, this is the function h, and this is the function s. Let me label those. So this is h, and this is s. And I can actually see there's 2 solutions to this equation that we're going to set up. But what's this thing here? So this thing that I put first on the graph is actually just the absolute value of t. So here I'll note that this is the absolute value of just t. It is a V-shaped graph. If you know the shape of this graph and you start altering the equation by adding or subtracting numbers, maybe multiplying by a value, you can use transformations to understand what the new graph will look like. Here's what I mean. If you're inside the function and you're changing the values of t, you have t minus 2, but this will have the opposite effect of what you'd expect on your graph. It'll take this thing and it's going to move it 2 places, not to the left, but to the right. Multiplying, now that we're outside the function, the y values by a negative, it'll take the graph that's here and flip it upside down. In terms of order of operation, the last thing that happens is the graph goes up 3 places. So this spot goes here, and we have this upside down V-shaped graph. So you can actually think of how this point travels. It goes 2 to the right, the graph flips upside down, and it goes up 3 places. Anyways, all that being said, our ultimate goal is to figure out, well, where does h of t equal s of t? Again, I'll write down the equations to solve this. And our goal is to solve this equation for t, and there should be two solutions. Just like with sine, the approach is going to be to get this part by itself. So I'm first going to subtract 3 from both sides of my equation. And we get negative t minus 2 is equal to negative 4. Now you can either multiply or divide both sides by negative 1, and that will change this to the absolute value of t minus 2 is equal to positive 4. So essentially, the negative cancels from both sides of my equation. How do you solve this thing, though? Because now we have an absolute value. You're not allowed to just add 2 to the other side. This symbol cannot be here if you want to do that. And it turns out you can actually break this up into two equations. The first equation is just ignore the absolute value and write t minus 2 is equal to 4. If you add t to the other side, you get 6. And that actually appears to be one of the solutions. The reason this works is because you're saying if you put a positive 4 here, will equal 4 after you apply the absolute value? And the answer is yeah. But what's the other equation that you can solve to find our other solution? The trick is to take the thing inside the absolute value and set it equal to negative 4. The reason is if you put negative 4 here, it'll become positive 4 after you take the absolute value. Again, if you add 2 to both sides, you get negative 2, and that is definitely the location of this spot here. Excellent. We have our two solutions. There is one final part to this. It says, can you use this to determine where h is greater than s? So here's h. Where are the y values of this function greater than these y values? It's either going to be between these two numbers or on the outsides of those two numbers. And just by looking at the graph, I can see that we're talking about this part of the graph. These values of h are all above these functions of s. So the answer is, if you want to know where h of t is greater than s of t, it's on the interval from negative 2 to positive 6. We will not include either negative 2 or 6 because there was no equal sign on this part of the question, and that's it for this problem.